So after presenting the vision, it's good to see what we've done so far. A big part in the last year in collaboration with the Aemo and the project that Alistair have greatly described. The first big thing that we'll be releasing imminently is the PSCAD network import. So you can see as this example here, the IEEE 39 bus system that is being imported to HyperSim. We really cover almost everything. So we have component placement, component rotation. We can already set all the parameters and all the components. We can really, once imported, run the load flow, start the simulation, and start getting results. Everything is being imported in details, and you'll see it's been almost surprising to us too. I mean, different simulation tools sometimes have different types of equations, algorithms, solvers that they use. And so far, we have results that almost perfectly match. If you want to have more information, I invite you to watch the full demonstration that we uploaded in our on-demand video library that's called From PSCAD to Real-Time with HyperSim. And you can see a live demonstration of this import and the results that we get. Second, is kind of a subtopic of the PSCAD import is the focus that we've done on generating plant import. This is obviously a huge challenge with the entire East Coast network of Aemo that needs to be imported with all the manufacturer plants with all their details, and also including, this is the biggest challenge, all the DLLs. So there are such examples here like measurement for PMU, high-level PAQ control, wind turbine local measurement, local control, and even converter control. All these DLLs being necessary to run a single plant, and there are hundreds of them. And these DLLs may run at different rates. They may have different execution time, different loads. The challenge is also that there is no such standard today to define the interfaces and to define how DLLs should be best optimized for performance or for ease of integration. So we needed to develop a solution that's able to be flexible and open and adaptable to be able to import automatically the plants and their DLLs, and eventually also run co-simulation, which will be the topic of my next slide. So to achieve the capability of simulating the entire Australian network or the East Coast network in real time or close to real time, I'll get to that later. We needed to add the capability to HyperSim of orchestrating this simulation. This is a technology that existed in RT Lab already for almost 15 to 20 years. That is based on publish and subscribe mechanism. That's domain-based strategy to logically separate the simulated systems. That's data-centric for ease of integration and interoperability. That has, and that's very important, a very low latency communication system to leave the most room for actual execution of electrical computation and control computation. That's also can handle synchronous and asynchronous modes, so like multi-rate with iteration, interpolation, compensation to be able to manage the rate changes. And that eventually also allows a dynamic connection and disconnection of components during the simulation. So this is a very important piece of architecture that will enable not only the co-simulation with DLL, but also several other interconnections, as Jean mentioned in the previous presentation, eventually with FMUs, with the oil and gas networks, with thermal models, with custom models, so many different other tools or other means of implementing models that could be integrated and co-simulated together with HyperSim or RT Lab. So this is how we get to achieve simulating the plants and the entire AEMO network. So we do have a real-time simulator that's dedicated to simulate the power system or the plants, and we have dedicated systems for the DLLs. And why is that separated is also that we need to be able to optimize the PC technology for the different loads. So the power system, for instance, does not have the same requirements as the DLL to achieve the best performance. So decoupling this using Orchestra, using this fast 5 gigabit per second communication link, it allows us to dedicate and choose the right technology to simulate either the DLL or the power system on the different PC. And that brings us here to the system that's still in production, that's almost ready to be shipped. So we have 128 cores with redundancy to be able to simulate the full power grid transmission and distribution, as well as synchronous and non-synchronous generators and FACS. So what Alistair presented earlier. And we have 24 PCs of 16 core with some redundancy as well. So that's almost 400 processors in total to execute the PSCAD DLL computation. And the challenge, as Alistair mentioned earlier, is to achieve the real-time performance is dependent on the raw performance and the DLLs. And this is where we really saw a challenge. I mean, the DLLs have not necessarily been designed or optimized for real-time simulation. Sometimes DLLs that should take quite short to simulate, they take a lot more time than would have expected. So we really needed to find PCs with a very high clock speed that are best for a single processing, to have DLLs run at the fastest speed possible, to be able to reduce the global burden of the simulation, so that we can achieve, in this case here, no slower than 3 times real time. But their only dependency to achieve real time is actually the DLLs. So this is also where we see that eventually would need to have a standard like a CIGRE Road Group B482 to define the best practices to develop DLLs to achieve the best performance for co-simulation. And this entire system will then, in the end, show a whopping 500 cores in the same simulation with redundancy to be able to maintain full-time simulation all day, all night, all weekends, to ensure the best performance possible, to reduce the time to market of new connections as described by Alistair. To achieve that, we've worked a lot on PSCAD, as I mentioned in the earlier slide. I'd like to remind the vision or get back on what Jean was talking about, the vision of having a single source of truth database, something that we've worked on already for quite a few years, with a standard definition for EMT and phasor data. So far, in terms of third-party software, we already have several interfaces like EMTP that's today not yet available through the DB, but that will still be a plan to bring it to our unified database. PSCAD, which is will have an imminent release, has been the focus of our work for the last year. We have PSSE Power Factory that are already available, and SIME also, but not through the DB. Those are all third-party software that we're able to bring data to OPAL-RT tools. For 2022, we're already starting a collaboration with the US research labs for GridLabD and GridPack that will also bring data to our DB. And we still have under consideration ETAP in the future. On our side, there are a lot of tools actually. And the main point of having this database, or one of the main points, is to be able to standardize the data formats of the models, to be able then to bring this information to our different solvers or software platforms like our FPGA-based electrical toolbox, or HyperSim, which is the main focus here with the Aemo project, or even ePhaserSim, our CPU-based electromechanical toolbox. We want to be able to bring this data to these different platforms with the minimum amount of maintenance work. In the past, I mean, we would have had to maintain several different scripts from each of the third-party software to each of our solvers, but having this centralized, unified database makes it much, much easier to move from one world to the other, from phaser to EMT, back and forth. And actually, the next very large milestone that we will have should be early next year. That will be our EMT to transient stability, or EMT to RMS conversion. So this arrow here, that will actually allow going back from our tools to external third-party software. So the first we're going to focus on is PSSE. So we will achieve by early 2022 the topic of a single source of truth database where our clients will be able to have a single source of data to manage their models, both in PSSE and HyperSim. And that will be a great achievement that we'll show very soon. And eventually we'll also roll out this capability for all other OPAL-RT platforms and also third-party software. We want to be able to go from any of these tools back and forth and have a single source of truth of data for the models. Also, in regards to the connection simulator tool, this is just a quick view on a high-level architecture where we do collaborate with Microsoft at the moment to bring our capability on the cloud and leverage all the tools that John has spoken about earlier, data analysis, neural networks, and so on. So how we see it so far is to have a user that log in with the Windows virtual desktop client and that connect to a broker that will manage the authentication through the Azure Active Directory domain services, to allocate then a virtual machine that would be either dedicated or pooled. And then the user would be able to map the target and the host, so be able to leverage several virtual machines, scale the targets to be able to parallelize not only the computation as we normally do with HyperSim, but eventually also parallelize the testing. So to launch several testing campaigns in parallel on virtually unlimited resources thanks to the Azure cloud. And obviously also have administrative processes, all the data privacy, security, all of this that we've talked earlier will be implemented to ensure that we have a very secure platform that decuplates the capabilities of our simulation systems. So in conclusion, the path to the digital twin will need the participation of integrators and manufacturers in the concept of the digital twin, because it will be important to provide the precise model of the plants. Otherwise, online model identification will become necessary if integrators or manufacturers cannot collaborate, are not available to collaborate to be able to achieve a precise model and also have a good understanding of the and a good integration of the manufacturer DLLs for the plants. It's very important, as we mentioned many times today, to generalize the usage of a standard for controller DLL implementation. Like the CIGRE work group before 82, they're working on this, the real code. The migration of simulation software to the cloud will also be essential for data management, model analytics, grid data analytics, grid data processing, all the tools that John has talked about. Will also be very important to leverage clusters of high-performing multi-core computers, not only to parallelize model execution, but also testing of several contingencies at the same time. That will be crucial to achieve the update of transient stability assessment every 5 to 10 minutes as required by the control centers. And in all that, OPAL-RT is committed to develop a platform ensuring data privacy and confidentiality, as well as cybersecurity to address strict utilities and agencies policies.